Hey, it's Mr. Shrum, and I'm going to walk through the course activity called Exploring Forces. And really, we're just identifying and sketching forces that act on real-world objects. And to break that down further, we're going to develop and use a model to describe what's going on. And what's going on, we call that phenomena. We're also going to construct a scientific explanation based on reliable evidence obtained from an experiment. And in the introduction, we talk about every day we see things in motion. And we usually associate motion with something being pushed or pulled in a certain direction. And that push or pull is called force. And these forces can set an object in motion and make objects speed up or slow down. So we are going to explore different types of forces. And here are some of the key ideas to keep in mind. A force always involves two objects. One object is exerting a force on another. A force has a direction and an amount. So you'll always have these two sets of information. So how much of a force, and then where is it being pushed or pulled? Arrows show the direction of forces in a diagram, and force exists between two objects in contact and also between objects at a distance. So here's task 1. Contact forces. And in part A, it says set the ball and barrier about 2 feet apart on the table. Now we don't have the equipment for this, but we can still use the pictures and talk about what would happen. So you have a ball here and a ruler. And if you were grabbing both ends of the ruler and push the ball with the ruler, the ball starts to roll, it hits this barrier here, and then it bounces back, rebounds. Describe the motion of the ball as it moves. So it's really easy. You just, it says the ball rolls, hits the barrier, and then turns back or reverses direction. Part B, identify the forces exerted on the ball from the time the ruler touches it. The ruler exerts a force on the ball. So you're using the ruler to make the ball move, and then the barrier exerts a force on the ball, and that force makes the ball change direction. And then lastly, you have the table exerting friction on the ball. So you have the force from the ruler, the force from the barrier, and the friction between the ball and the table surface. Part C, the force of the ruler on the ball is called an applied force. So you're applying a force to the ball to make it move. The force of the barrier on the ball is called a normal force. And both of these forces are exerted by surfaces, and the direction of force is at a right angle to the surface. The difference is that an applied force is exerted by moving an object. A normal force is exerted by a stationary object. So an applied force, if you're moving something to move something else, that's applied. If something is stationary and then exerts a force, it's normal. And it says to draw 2 arrows, and this is the arrow, the direction of the force. The ruler pushes this way with the force. The barrier is pushing the opposite way. Now explore friction force. Set the piece of plastic or wood on the table. Push it steadily across the tabletop using your fingertip. Note how much opposition to your push you feel. Now repeat that with the piece of plastic or wood across a rug, carpet, or piece of fabric. So if you were to do this, you would notice that the object would move more easily on some surfaces and it would be harder to move on others. So the opposition to motion is greater on the fabric than on the smooth tabletop. Friction force is the opposition to the motion of surfaces sliding across each other. Based on your observations, what is one factor that affects the amount of friction? One factor that affects friction is the texture of the surface on which an object moves. So if something has lots of bumps, and like say gravel, it would be harder for something to move or glide across than it would be like on a basketball court or a slide, something very flat and slippery, very smooth. That would be easier to move on. So now we're going to draw an arrow to represent the friction force. So here's the table, here's the piece of wood, and you're pushing it to the right here. The friction would act in the opposite direction of the force, the movement of the object. And then part G asks you to list several examples of applied force, normal force, and friction. So some examples of applied force: if you kick a soccer ball, if you hit a racket with a tennis ball or a tennis ball with a racket. A normal force example would be a dropped glass shatters on the kitchen floor, and then magazines or books just resting on a table. Friction force examples: a rubber tire propels a car. The sole of a shoe prevents a person from slipping. So those things, you need traction, right? And if wheels were smooth and there wouldn't be as much traction, right? So if the roads were smooth, the tires are smooth, there would be a lot of gliding and slipping, similar to how like hydroplaning works. But the tires will grip the road, and you get a lot more traction that way. The next part deals with contact forces. Again, hold a flat piece of paper horizontally, lift it high in front of you and drop it. Then crumple a piece of paper into a tight ball, hold it high in front of you and drop it from the same height. Compare the motion of those two pieces of paper. So if it's flat, it will take longer to fall. It moves from side to side as it falls. But if you crumple up paper, it falls quickly. Part B, when an object is moving through air or water, the air and water molecules must move aside, and that creates a force that opposes motion. We call that resistance or drag. So knowing this information, why does that flat sheet of paper take longer than the crumpled ball? The flat piece of paper has a larger surface area. So more and more molecules of air have to get out of the way when it's moving. So it meets more resistance than the crumpled paper does. When pulled, stretchy objects such as rubber bands exert elastic force. Gently hold one end of the rubber band and pull on the other end. You will feel the rubber band pulling back. How does the force exerted by the rubber band change as you increase its length? What do you observe? So the more you stretch that rubber band, the more force it exerts. That's the thing about elastic force and elasticity. The more stretch there is, the more force. Tension force refers to an object being pulled tight from both ends. So think of having a string or rope and then pulling on both ends of that rope. That type of force is only exerted if the string is really tight or taut. Grasp the two ends of the string, pull them so the string is taut. How does the force differ from elastic force? The string does not stretch measurably when the tension force is applied. However, an elastic material would stretch if it's pulled. So tension, there's no stretching. Elastic force, there is stretching. What are some examples of drag, elastic force, and tension? Drag force, an example would be a parachute. There's an air drag on a parachute, kite, car. And if you're in a boat, the water drag is a good example of that too. Elastic force, bungee cord, trampoline, bow and arrow, slingshot are all examples. And then tension force, you have window blinds, a tension bridge, and then furniture that's made from certain materials like nylon or wicker. And then lastly, we have forces exerted over a distance. And this one's about hangers. Take one hanger, place a hanger on each of its end like this. If your hangers aren't notched, wrap tape around the hooks to hold them in place. Does the system of hangers balance? Why or why not? So this system does balance. There's an equal amount of weight on both sides, and the two hangers placed on the first hanger are equally spaced from the center. Now add a second hanger to one of the sides. What happens, and why does the system behave the way that it does? What is the name of the force responsible for what you're seeing? So it would tip down on one side because you no longer have a balance of forces, and that force is gravity, the gravitational force. There's more gravitational force on two hangers than on one hanger, so that side gets pulled down. And here's the diagram for part C. You just draw those arrows, and you would draw this arrow to be longer, meaning it has more force, more gravitational force on this side. And then we have magnetic force in part D. If you have two magnets, you can try it yourself, but I'll show you the example answers for these as well. Explore three possible combinations. In two of the combinations, the two ends are the same. In one combination, the two ends are different. Describe the force you feel in each combination. If the two ends are the same, the magnets push away from each other because like magnets repel. And when the two ends are different, the two magnets attract each other. Part E talks about electric force. Blow up the two balloons and knot them, then tie a thread onto each balloon. Suspend these two balloons using tape so that they're about 6 feet, not 6 feet, 6 inches, so half a foot apart, and check that they don't move or interact. Rub both balloons with wool or fur. If wool or fur is not available, rub the balloons on your own hair. Do they attract or repel each other? They both repel each other. Now you can rub one balloon with wool, fur, or hair, and the other balloon with a piece of plastic wrap. And then do the same thing, and now they attract each other. Part G is asking for examples of gravity, magnetic force, electric force in everyday life. Gravitational forces are things like waterfalls, rocks moving downhill, slides. Magnetic force examples, refrigerator magnets, conductors, electromagnetic conductors. There are magnets used in that as well. Electric force, static cling on clothing, when you do your laundry or you wear socks and you walk on carpet. There's a lot of static cling. And then small shocks from metal doorknobs. If you wear socks and then rub your feet on the carpet and then touch a metal doorknob, there will be a small shock. And then part H just asks, what is one question that you'd like to investigate further about forces? So there's lots of questions you can ask here. How does the shape of a car affect air resistance? Will two balloons rubbed with plastic wrap repel each other? Anything like that will do. All right. And that's the end of exploring forces. I hope this helped, and I'll see you next time. Bye-bye.